Composing transpositions this way lets you generate a sequence of transpositions U, TU, TTU, TTTU. The period of this sequence is the same as the period of T. For a block size of 12, the longest possible period occurs when the lengths of the cycles are 3, 4 and 5, namely 3 times 4 times 5 equals 60. If your messages are longer than 60 blocks, you may want a longer period. This can be done by permuting the transposition with either U or T in some repeating or random pattern, say U, TU, TTU, UTTU, UUTTU. This can generate a very large set of distinct transpositions, provided that T and U individually have long periods, and the cycles of T overlap the cycles of U, as described earlier. You can test whether the cycles overlap sufficiently by using the accretion test. Start with any one of the cycles of T or U. This forms a set containing just that one cycle. Add to this set any other cycle of T or U that has elements in common with it. Now add to this larger set any other cycle of T or U that has elements in common with the cycles you have already chosen. Continue this way until there are no more elements in common. If the set of cycles now contains all of the cycles of both T and U, then you have good overlap. If you decide to use more than 2 transpositions, say T, U and V, then T and U should overlap, T and V should overlap, and U and V should also overlap. Here is an example using some transpositions from earlier in this section. T equals brackets 1, 4, 7, 12, 3, brackets 2, 10, 6, 9, 11, 8, 5, and U equals brackets 1, 10, 8, brackets 4, 6, 5, 12, brackets 2, 11, 9, 7, 3. Start with the cycle 1, 4, 7, 12, 3. This has the element 1 in common with the cycle 1, 10, 8 of U, so add that cycle to the set. This has the element 4 in common with the cycle 4, 6, 5, 12 of U, so add that cycle to the set. And so forth. Since this will include all of the cycles of T and U, they are a good overlapping pair of transpositions and will generate a very large family of transpositions when they are composed. Section 7.8. Halving transposition. Halving transposition is a computer technique I invented that uses a binary key to swap units that may be either bits or bytes or possibly hex digits. IBM published this in the company's Invention Disclosure Bulletin, and it was considered for possible inclusion in the Data Encryption Standard, DES. Halving transposition operates on a block whose size is some power of 2, typically 32 or 64 units. For a block of n units, the key will have n-1 bits. Let's use a block size of 16 characters as an example. The plain text is George Washington. The transposition will use a 15-bit key. The first bit of the key determines whether the left and right 8-unit halves of the block are swapped. A 0 means no swap, a 1 means swap the halves. The next 2 key bits determine whether the 4-unit halves of those halves are swapped. If bit 2 of the key is 1, then the first quarter of the block is swapped with the second quarter. If bit 3 of the key is 1, then the third quarter of the block is swapped with the fourth quarter. The next 4 bits of the key determine whether the halves of those quarters get swapped. For example, if the fourth bit of the key is 1, then the first eighth of the block is swapped with the second eighth. The final 8 bits control whether the 16th of the block gets swapped. For example, if the last bit of the key is 1, then the last 2 units, the 15th and 16th units of the block, letters O and N, are swapped. To decipher this transposition, the steps must be done in the reverse order. That is, the individual units should be swapped first, then the pairs, foursomes, and so on. Section 7.9. Multiple anagramming. A general technique for solving transposition ciphers, one that works with many types of transpositions, even when the type is unknown, is multiple anagramming. To use the technique, you need to intercept several messages of the same length. If these messages have been transposed with the same key, then the first letters of each message will end up in the same position in all of the ciphertexts. The second letters will end up in the same position in all of the ciphertexts, and so forth. We can exploit this fact. Make paper strip 1 with all of the first letters in the ciphertexts. Make paper strip 2 with all of the second letters in the ciphertexts, and so forth. Make as many strips as the length of each ciphertext. These strips can be matched up just the way we did when we solved a columnar transposition. The more messages that are available, the longer the strips will be, and the greater the chance of success. It is generally felt that a minimum of 3 messages are required. Let's look at an example. Suppose we have these 3 cipher messages. The message length is 12. The 12 strips are shown to the right. Message 1 contains a K. Some likely letters to precede that K are C and N. Message 1 contains 1 of each. Message 2 contains a D. A likely letter to precede the D is N. Message 2 contains 1 N. Let's check that these are plausible choices. We have. In message 2, the most likely letter to precede ND is A or E. This gives 3 possibilities. Matching each of these 3 choices with the remaining 9 strips, the best match is with strip 4. This matches up well with columns 5 and 10, which we had already combined previously. The 3 messages are now easily completed. 1. Attack at dawn. 2. Send more ammo. And 3. Meet me at once.